Hi everyone, I'd like to welcome you to the Carl Sagan Center Colloquium Series, and thank you for coming today. Before I introduce today's speaker, let me just tell you a little bit about the series. We have these talks every Wednesday at lunchtime, so I encourage you to come to as many as you're interested in and your schedule allows. You can find the whole schedule on our website. You can go to www.seti.org, click on the picture of Frank Drake that says Scientific Lectures, and that'll get you right to the Colloquium homepage. And from there, you can sign up for our email list to get notifications every week of upcoming talks. You can also view the video archive of talks. So if you happen to miss a talk in this series, in about a week or two after each talk, we put up a video as well as usually the PowerPoint or the slides from the lecture. So you can follow along and listen to and watch the lectures from the comfort of your own computer. And so you can go and get all those archive videos right on that Colloquium homepage as well. And so because we do record these talks, I'd like to encourage you to try to hold your questions until the end of the talk, and then wait until I come around and give you this microphone. As you can see, this microphone doesn't amplify your voice, but what it does is it captures your words for posterity so that they can go onto the video archive. If you ask questions during the talk, then usually the microphones can't capture what you've said, and so there's gaps on the audio of the talks, which can be annoying if you're watching them later. So I encourage you again to hold your questions until the end, if you can. So let me tell you about next week's talk, which will be on April 8th. That will be by John McCarthy, who will speak about convergent evolution of our own and extraterrestrial intelligence. So that should be a very interesting talk as well. But today I have the pleasure of introducing Rachel Mastrapa, who's at the SETI Institute and NASA Ames Research Center. Rachel received her BS in Astronomy and Earth Sciences from the University of Southern California and her PhD in Planetary Sciences from the University of Arizona. And she's been at the NASA Ames Research Center since 2005 and a PI at the SETI Institute since 2007. And she's a member of the astrochemistry group over at Ames doing all sorts of exciting laboratory work. So Rachel is going to tell us about some of her results today.
Thank you. But right before, I don't know if you've heard about some exciting news from VIMS, Cassini, the instrument on Cassini. There's a new discovery. I don't know if you've heard there's multiple organics found in the Enceladus plume. They've found a new organic and also some new activity on the surface. Here's an image of the surface. It looks like in the hard economic times, they might be looking for new sources of ethanol. And I can't confirm this, but I've heard the high-resolution images have show some evidence of graduate students. But anyway, I wanted to thank Adrian for the auspicious date of my talk. So now that that's taken care of, I'll talk about my actual research. And today I'm going to talk to you about weathering on icy satellites. And most of my lab work involves infrared spectroscopy. So I'm going to be focusing on how infrared spectroscopy tells us what's going on the surface of these satellites. And I also would like to thank the astrochemistry group and my other collaborators at NASA Ames. So this is the big picture question that kind of frames where my research goes, is what is the composition, or at least the original composition of objects in the outer solar system, especially the icy ones. That's my focus. And so I did say satellites, but that also includes the dwarf planets and Kuiper belt objects, that sort of thing. I'm just looking at icy objects in general. So the problem is, what are these original composition? And of course, we want to be able to detect that remotely, because as of yet, we can't go there. And the method that we use for detecting the composition of these surfaces is infrared spectroscopy. However, the part of the surface that we're seeing is the first millimeter to centimeter of the surface, which is exposed to vacuum and radiation, and so could possibly be very heavily processed. And so, for example, I have here what an object in the outer solar system could be made of. This is a deposition condensation sequence from, imagine if you have a cloud of gas that includes all the starting materials of the solar system. As the temperature decreases, this is the order that the materials would deposit in. And so as you go down from 150 Kelvin, you start with water ice, and then ammonia and water, and methane and water, and then when you get really, really cold, you get methane and hydrogen. And so in the outer solar system, you'd expect to see this sort of group of materials if this is representative of the original composition. However, if you look at a spectrum, and this is just kind of an example spectrum of an object in the outer solar system. This is Ganymede, the moon of Jupiter. And this is an infrared spectrum from 1 to about 5 microns, or if wave numbers, if that suits your fancy. And most of these features are water features. These large humps right here are all water, 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 water. So that agrees with the condensation sequence. But what we don't see very commonly here, or even farther out in the solar system, is as much methane or ammonia as we'd expect to see. Now, but what we do see is carbon dioxide. That's this little feature right here. Carbon dioxide happens to be extremely common on a lot of these objects. So this isn't necessarily the original composition. Well, obviously, this is not the original composition. What's happened? How does it get there? How did it change in composition? And also, what other things are going on that might not just change the composition, but might be changing the physical properties of these materials as well. So how we'd like to be able to answer this problem is identify what the processes are on these surfaces, determine the relative strengths of these processes, and then what the end results of them are. Are they chemistry, or are they actually changing the physical structure of these materials? Figure out all of that, and then basically reverse everything to try to figure out what the original composition is. And so you're essentially just reversing weathering. Weathering is a concept that's really common on the Earth and well, reasonably well understood. This is just an example of an obsidian rock that has been weathered. So, and a very, very old penny for scale. So this object, this part right here, the really dark part, well, first I'll show you the white part. This is the weathering rind. And then basically someone just took a rock hammer and took a chip off of it, and this shows what the inside looks like. And so this is pretty typical. If you go outside and find any rock sitting out and look on the outside, if you knock off a part of it, the inside generally looks very different. And of course, this is looking different to the eye. So this is just visually in the visible wavelength that may or may not mean that there's any actual chemical changes that have taken place. But it also has been shown that the weathering on Earth, which includes which is mostly dominated by interaction with liquid water, also changes the mineralogy of the surface. And so often, if you want to really know what a rock is made of, you don't want to look at this junk on the surface. You want to knock off a piece and look at the inside, and that's where you'll see what the original mineralogy is. Unfortunately, we don't have the capability of making a really giant rock hammer and going and knocking off a piece of an icy satellite to see what's on the inside. So instead of doing something like that, we have to try to understand what is exactly going on. And at the same time, is it even appropriate to treat ices as a rock? Well, if you go to the most basic definition of a rock, it's a solid, naturally occurring mass of matter composed of mineral grains, glass, altered organic matter, or combinations of these components. So that's a very broad definition. And I could make the argument that, organic matter is seen on a lot of these objects. Even the one spectrum I showed you had CO2, but they often find other complex organics. Some ices are found in a glass phase sometimes. And also, for minerals, a mineral is simply defined as a naturally occurring homogeneous solid with a definite chemical composition and a highly ordered atomic arrangement. So if you had an actual individual crystal of water ice, that would meet this definition because it has a fixed chemical composition and either a cubic or hexagonal mineralogical arrangement. And so technically, you could treat ices like a rock. And when I've discussed this with people before, they've also pointed out to me that anyone that enjoys a drink or two knows that ice has been thought of as on the rocks for a long time. However, the process, the environment, when you compare Earth to space, ends up being very, very different when it comes to weathering. On Earth, like I said, it's really dominated by liquid water. And this includes, with liquid water on the Earth, this includes both chemical alteration. Say if water gets into your material, it can change a basic sandstone into sandstone and clay and that sort of thing, and wash away some of it and that sort of, but also it physically weathers something. It'll roll a rock through a river and break it up into pieces, and so it both chemically and physically alters the material. And also, luckily on Earth we have air and wind, and those also can alter the surface of, alter the minerals, partly by, again, chemically and physically. Chemically, you've seen there, you may have seen rocks that have been oxidized on the outside, and also the wind can physically break materials up. If you've ever been out in the desert in a stiff wind, all the sand is blowing around, and that material can end up being very broken up. And sand is often predominantly quartz anyway, since all of the other minerals that are physically a lot weaker have just been broken down. And so that's those are the main factors on Earth. Now, out on these icy satellites, there is generally absolutely no liquid water. So that's not really an option for the kind of weathering that we're looking at for. And only in a few cases are there a stable atmosphere at all, or a very thick atmosphere, such as on Titan. So wind is only found on one icy satellite. But in general, the main sources of weathering are radiation and thermal variations. And how, let me define these for you. Radiation still can technically occur on the surface of the Earth. It's just not as strong with it, since we have the atmosphere that scatters out most of the radiation. It's just not as effective as on these objects that have thin or absolutely no atmosphere. And so this ends up being a major factor, especially for that thin surface, the first millimeter or so. And by thermal variations, of course, rocks are responsive to thermal variations, but not the ones seen on the surface of the Earth. It often takes several hundred degrees to actually melt a rock. While, as you'll see, as you saw in that condensation sequence, the temperature out in the outer solar system, a lot of these materials can actually just sublime and recondense regularly. Finally, this is a general catch-all, mechanical weathering, and that includes any of the large-scale processes, volcanism, and what ends up being extremely important in the outer solar system, cratering, those kinds of processes that, of course, have some kind of effect on these materials, but aren't necessarily well constrained. Go ahead.
Two questions. Under Earth, it seems microbes interact with that aspect of the rock a lot.
Right.
They eat it, they churn it, and also they desiccate it with waste sometimes. And then
Yeah, the comment was that microbes also are a component in weathering. I kind of threw that in with liquid water. Go ahead.
Okay. And the other thing about water, you mentioned liquid water. My understanding is that the freezing and thawing of water can really do great damage.
Right, yeah.
That's all the way down, but then in fact that is thin at the surface and it continues.
Right, and that would be
Is that mechanical?
Yeah, I throw that into mechanical. Like these are kind of loose groups anyway. But yeah, you're absolutely right. The comment was that the sometimes diurnal, sometimes seasonal freezing and thawing of liquids can physically break up rocks and minerals and that sort of thing. And it can have an interesting feedback, because while it's liquid, it breaks down the minerals, and then when it freezes, everything that's already soft begins with just fractures, that sort of thing. But yeah, that's a very common weathering process. But again, since liquid water is not stable on any of these surfaces, they're not going to see that kind of activity. I'm talking about in the outer solar system. So when talking about the mechanical processes, that again throws in just general large-scale activity. And as you've seen before, this now famous picture of the geysers on Enceladus. Of course, all of these material rocketing out and settling down is going to have some kind of effect on the surface. But and also there's general geologic activity, the possible cryovolcanism on Titan, and basically there's the huge, large tiger stripes. There's vents coming out, but there's motion on them, like strike-slip motion. So the material's grinding together, and that's probably going to have some kind of effect. But these features are large scale, or very large scale, and may or may not have an effect that we can see on that millimeter to centimeter scale. So I'm not going to be talking as much about these large-scale features, but it would be something eventually, once we kind of work out some of these other, answer some of these other questions, is to try to see if any of them are tied to large-scale activity. So going back to the main weathering processes on these outer solar system objects, we have radiation, thermal variations, and mechanical. And again, I'm not going to talk about that one as much, but to list kind of the things that happen with the mechanical stuff. You get material that's transported around, you get material that's eroded off of a surface, so maybe that's how you can see a nice clean surface. You get accumulation of material carried in from someplace else, and maybe perhaps you get some kind of chemistry. And I threw that one in because there could be some amount of impact-induced chemistry. And this is at multiple scales, either very large scale, there's a gigantic object, or you can have some amount of micrometeorite overturning the surface and heating it just enough to have some kind of chemistry going on. But again, that's the kind of that's the large-scale category that I'm not going to get into in this presentation. Instead, I'll talk about thermal variations. What I mean by thermal variations are just the slight changes in temperature, either diurnal or seasonally, that might be seen or across the surface of an object. And what this could cause is, for example, migration. So say on Europa, the poles are colder than the equator. The more some of the material can sublime from the surface and eventually get trapped in the poles because the poles are significantly colder. So you can get migration of materials, general sublimation, and by sublimation here I mean just complete loss. If it comes off the surface and manages to escape, you end up losing some material. And then possibly chemistry, maybe it gets warm enough for things to actually interact, but this sort of solid state chemistry is really, really unexplored. And finally, radiation. Now, it's been shown for a long time that and it's been studied mostly in the interstellar medium, that radiation can process ice and very simple organics into complex organoids, PAHs, that sort of thing. And so you'd want to start with different starting mixtures to really simulate the solar system objects. But in general, what you can do, what it's shown is that when you irradiate a surface, you can build more complex organics. And then some materials often just kind of completely disappear. For example, ammonia, when exposed to radiation, just breaks apart very, very quickly, which I would actually goes over here under dissociation. And also, radiation induces spallation, which basically involves the radiation coming in and just kicking the molecules off of the surface. So you end up losing material that way. And finally, there's been a lot of work looking at phase changes. Some of the ices can be found in different orientational states. So for example, water has several crystalline phases and then also an amorphous phase at low temperature. And if you irradiate the crystalline phase, it converts to the amorphous phase. And I'll be talking about that more later. Because actually today, of all of these categories, I'm going to be talking about sublimation and the phase changes that can be induced. So as you can see, there's a lot of different parts of this that need to be worked out. And our group has worked on experiments that just cover a couple of these little categories that I'm going to talk about today. So first with sublimation. To be able to understand how often materials lost from the surface, you'd want to know something about the surface residence time that these materials have as a function of temperature. So we did experiments to calculate the surface binding energy. So this slide's a little bit busy, but this is work that Scott and Lou did back in the 90s to calculate the surface binding energy. That's this guy right here. And so if you write out the residence time as a function of the frequency of vibration of the molecule that you're looking at, temperature, you get a Boltzmann's energy constant, and you can back out the surface binding energy from this equation. And the way we do it is we can observe the infrared spectra of these materials in the lab and look at either single component materials or multiple component materials. With a single component material, we have to track the change in the size of the band with time, and we can back out the average binding energy for the surface. If we do multiple components, say, for example, does methane stick better by itself, or is it possible that if there's water present, will it stick more efficiently? We do a multiple component process, and there's a slightly different equation where we look at the amount of time that it takes for a monolayer to deposit. And I'll go through each of these and explain how we do the measurement in detail. So in this case, like this, if you look at any of these old papers, they did a large amount of different materials, including carbon monoxide, carbon dioxide, ammonia. But this time we decided to look at methane. And so using our lab system, we have the ability to get down to very low temperatures and very low pressures. And this is an example of one of our sample chambers, either a schematic and the real image. And what it's showing right now is a photolization, which is not what we did for this experiment. And usually the spectrometer is blocking the view here. But what we do is we deposit an ice on a sample window, and the beam of the spectrometer passes through the window, and we can look for variations in the spectrum with time and with changes in temperature. So for example, when we did just pure methane ice, we would deposit methane at a very low temperature and take a spectrum. And these are the two main bands in this spectral region. This is around 3.2 microns, this is 7.7 microns. These are the two main methane bands that we would deposit at 10K. And then we'd just heat it up and watch the band shrink as the methane sublimed from the surface. So it's relatively straightforward, and we did it at 3 different temperatures. And so this is the area of this band right here. This is calculated area. And at the highest temperature here, 39K, it took only 20 minutes for the entire sample just to sublime right off the surface. And so we did it at 3 different temperatures and plugged it into that equation that I showed you earlier, and we get a number. And fortunately, it agreed between all 3 of these different experiments, which is always nice. But and so that's how we calculate this. And so this binding energy is an average binding energy, because the ice sample is sitting there in vacuum at a particular temperature, and the molecules on the surface are hopping off. But some are staying, as usual, it's a Gaussian distribution. And so some are hopping off faster and some are hopping off slower. But since we're looking at it coming off over a period of time, we're seeing the average as it all tails off, we end up getting the average number. This is important because with the mixed components, we end up getting the maximum residence time. So when we do a mixture of components, we wanted to see if methane was useful for making water stick. Water was useful for making methane stick a little bit better. And so what we do is we make a mixture of water to methane at a ratio of 20:1. The reason to do this is to have methane isolated within the water. So it has to be a small amount of methane within the water, or else the methane is just sticking to itself, and that's not the measurement that we're looking for. And so this is a spectrum of both methane and water together. And these 2 features right here are the 2 methane features, while these large ones are all water. So what we're looking at is a sample that's mostly water, with just a tiny bit of methane in it. Now, unlike the previous experiment where we could just heat it up and sit and watch everything come off, We can't do that this time around because what we'd end up doing is just getting the binding energy of water because the sample's mostly water. Instead, what we did was take this mixture of 20-to-1 water to methane and deposit it at several different, slowly increasing temperatures. And essentially, at each temperature, we deposit and take a spectrum and measure the size of the bands and then ratio them to each other. And hopefully, we'd always get 20-to-1, which is our original starting composition. And so we normalize that at low temperatures. We're expecting 20-to-1. And so down here, we normalize that to 1. And then at slowly higher temperatures, we eventually get less and less methane at each deposition temperature. So what we're measuring here is we're in our chamber, we're putting in a cloud of gas that's in a ratio of water to methane, 20-to-1. And since it's mostly water, what's depositing the majority of what's depositing is water. So we're getting monolayer after monolayer of water. And we're able to measure that by using a laser and measuring the interference fringes as the layers are slowly depositing. So we get to count those interference fringes and measure the speed of deposition of the water. And so what is going on in there is that some methane sticks to the surface, and it's sitting there. And based on its residence time, it's either going to hop back off again, or it's going to be buried by the next layer of water. And so when we see one of these mixtures of water and methane, this is all buried methane. So this is all methane that stuck around long enough, that had a residence time long enough that it got buried. Because eventually at these higher temperatures, the methane is completely unstable. So as we deposit at higher and higher temperatures, there's less and less methane. Until right here, this is when we deposit the mixture and no methane sticks. And so the time that it takes for the next layer of water to deposit is the maximum residence time that methane has on that surface. So how we get that measurement of residence time is by measuring how quickly the water is depositing. So as opposed to an average residence time, this is a maximum residence time. So all the methane has hopped onto the surface and hopped off before that next layer of water can come down. And now, thank you for being patient with that long explanation. The main point, though, is that that number that we get for the binding energy ends up being higher. The pure methane binding energy is around 1100 K. The binding energy of methane to water for the maximum residence time is 1800. And so if you recalculate the residence times of these materials as a function of temperature, there is, especially at these low temperatures that you would see in the outer solar system, there is several orders of magnitude increase in residence time. So what we're saying is in the presence of water, gas phase methane can deposit at either much higher temperatures or much faster than methane would deposit to itself. And so this, again, this represents the maximum residence time before first hop. So this blue line is just methane to methane. And this red line is that maximum residence time. And then on top of this, so what we can say from this is that we could probably see methane in areas that your general idea of of gas condensation would tell you it shouldn't logically be. So it's possible that methane can hide in a lot of these places, and on top of that, this residence time is just for the surface. So if the water ends up burying some methane, it can last even longer on the surface. We haven't been able to calculate volume binding energies or anything like that. But if this methane gets trapped, it might be able to last much longer. And finally, since this is also the residence time before first hop on a tiny little sample, it's entirely possible that it could get to that it could take that hop and then recondense someplace else on a very large satellite. So if you really, these are just going to be average numbers to give you an idea of where methane can be stable based on temperature. If you have a specific object that you then know a lot more about its temperature variability and its long-term temperature stability, you'd want to do a full Monte Carlo simulation to say, okay, with each, and this is the binding energy, this is the maximum binding energy, and with each hop you have whatever statistical possibility for it to either escape into space or redeposit. So this, even though this is a maximum residence time, the methane could be able to stay on the surface even longer if it ends up hopping around a lot. So what we've shown in general is that if you just look at the temperatures of the objects, methane is stable. There's this ice line, the red line over there, an ice line for methane. But it's possible that with our numbers, it could, scoot it in before Saturn. And so it's possible that you would be able to bury and preserve methane for a long period of time in the Saturnian system. And also these numbers end up being useful in the Kuiper belt as well. This is some work by Schaller and Brown where they looked at the long-term temperature variations in Kuiper belt objects and showed that for the very massive objects, of course, they can keep all of their volatiles. And in this case, volatiles were carbon monoxide, nitrogen, and methane. That these objects very clearly kept all their volatiles. These objects would lose all of those materials. But then there's these objects that are right kind of on the boundary. And depending on their diameter, they may or may not have lost all of their volatiles. Now, some of them have actually shown observations that you can see methane on the surface. And so it could be that this stickiness of water can help explain why it's able to keep those materials. And eventually, if there are more objects that are close to this line, this could be an explanation for why they're able to see methane on the surface. So that is how sublimation and possible burial and redeposition can change how these surfaces are processed with time. The other process I'm going to talk about today is the radiation-induced amorphization of water ice. Now, as I showed you in that spectrum of Ganymede, it was mostly water. And a lot of the objects, especially the satellites, are almost all mostly water. You see these very strong water features. Water has this, water, for many reasons, is a really fascinating material, but it also has this interesting property that if it's deposited in vacuum below 135 Kelvin, it's in a glass phase, an amorphous phase. If you heat it up past 135 K, it reorganizes into a crystalline phase in an exothermic reaction. And once it becomes crystalline, you can cool it back down again, but it's an irreversible reaction. It will stay crystalline. So the idea has been that if you see amorphous ice out there, anywhere, solar system, interstellar medium, what have you, that the object you're looking at has been below 135 K, or since it's an exothermic reaction, even below 100 K for the age of the solar system, age of the whatever, for forever. But unfortunately, if you expose a crystalline surface to radiation, it can convert it back to amorphous. And this has been shown in the lab. Well, for one thing, you'd have to be able to detect the difference between amorphous and crystalline ice remotely. And so this is a near-infrared spectrum taken in the lab of crystalline ice and amorphous. And the main feature that everyone sees, this is at 75 Kelvin, the main difference is this feature here near 1.65 microns. That's the main one. But in general, there's a lot of general shifts where the amorphous features are all shifted to shorter wavelength in comparison to the crystalline features. And it's hard to tell in the stacked spectra, but the amorphous features are often a bit weaker than crystalline. And then if you do an experiment, this is my work from my dissertation, if you do an experiment where you combine where you take an amorphous ice, heat it up to crystallize it, and then irradiate, in this case with protons. But previous work that have shown that it just doesn't even matter what kind of radiation source you can use. You can use UV, you can use electrons, you can use whatever. You end up converting the crystalline back to a spectrum that looks like amorphous. Is it absolutely positively amorphous? It's not clear from infrared spectra, but they have done experiments with electron diffraction, where they've taken a crystalline ice sample and photolized it, and even the electron diffraction pattern looks like amorphous again. So either way, it either is amorphous or it looks like amorphous, and we would never be able to tell the difference from the infrared spectra. So to be able to analyze data from solar system objects, you need to be able to compare your observations to measurements made in the lab to see how to be able to quantify these shifts in the spectra. But of course, since the viewing geometry is so different, and for many other important reasons, you can't just take the laboratory data and compare it directly to the actual object. What you want to do is calculate the optical constants and then use those in a scattering model to actually fit the spectrum of whatever object you're looking at. And so that's what I've been doing for the last couple years, is I've been calculating optical constants. And this is the real and the imaginary part of the index of refraction. This is right here. It's a complex number. This is the real part, and this is what it ends up looking like when you separate it out. And that has to do with how, of course, is related to how the light bends in the material. And then the K part, the imaginary part, is related to what amount of light is absorbed by the material. So it ends up usually looking exactly like the absorption bands. That in this case, this is a mid-infrared spectrum of water. And again, these are the strong absorption peaks seen in the mid-infrared. And for the last couple of years, I've been working on calculating optical constants for amorphous and crystalline ice in the near-infrared and the mid-infrared. And this is all of that put together. And then I use the optical constants to create model spectra using a Hapke model of a large range of mixtures of amorphous and crystalline ice. So let me walk you through the near-infrared part. It's a little bit harder to see, but the red, this is a mixture of amorphous and crystalline ice at 100 Kelvin. The red is 100% crystalline, and the blue is 100% amorphous. So just like that figure I showed you earlier, the strongest band right here at 1.65 is 100% crystalline, and this one is 100% amorphous. So you can see it just gets weaker right there. And then this region right here is a blow-up of the region near 3 microns. This is the strongest vibrational feature in water, and it's pretty much unobservable from ground-based spectroscopy, but it's measured using spacecraft. And usually only what's able to be seen from ground-based observing is right around here, and there's a gap right here that's due to interference with the atmosphere. And so if you want to try to get try to assess the crystallinity from ground-based observing, you're pretty much stuck with looking near the 1.65 micron feature. If you have spacecraft data, you can zoom in here on the 3 micron feature, and from this scale, it looks like nothing's going on. But if you zoom in, this is the Fresnel peak. It's basically when the material is so absorbing that it ends up reflecting back again, and it essentially inverts the structure of the feature. And so usually the crystalline features are the strongest. And so again, at 100% crystalline, the peak is the highest right here. And it has this kind of triple peak structure where there's one strong here, another here, and another here. Now you compare that to the 100% amorphous, there's kind of maybe a little bit of structure here, but it's mostly just one kind of broad peak in the middle there, and it's again shifted to shorter wavelength. So, and then you can see the slow change as it gets more and more amorphous. You lose the structure right here, this gets weaker, and again everything shifts to shorter wavelength. So say we take a spectrum of Ganymede from NIMS that I showed you earlier, and we zoom in on that area and try to do a fit, we're trying to mostly get this area around here. I was able to put in a mixture of 30% amorphous and the other 70% crystalline, and get, for having just thrown this together, get a kind of reasonable match, although the actual spacecraft data is shifted to even shorter wavelength compared to my model. So that could speak to a bit more amorphous than I'm even guessing at, or it just needs a little bit more work. But in general, I'm getting a decent amount of agreement through here. And this ends up being rather tricky, because even though it's very absorbing here, this is a region that actually is transparent. It's a space between some of the bands. And this is where the largest amount of error is in the measurement of the optical constants. So I'd like to see what's going on here, but that's my largest amount of disagreement. But as you saw earlier, it's right around here that's showing you the difference between amorphous and crystalline ice. And you can see my mixture, my 30% amorphous mixture, is matching this little 3.1 peak reasonably well. And so this is kind of the beginning of a project that I was recently funded to do, to try to look at amorphous and crystalline ice on the icy satellites and possibly the KBOs as well. And so going back to these weathering products and the processes that are going on, that's just a couple experiments that have covered just a couple of these processes that are going on. So what we really need to be able to constrain how important these processes are when compared to each other is we need to have, from spacecraft data or from ground-based observing, we need to have a better idea of the radiation dose on the surface and thermal and the temperature of the surface, and also if there's a decent amount of thermal cycling, diurnal cycles, seasonal cycles, and also temperature variation across the surface. And so really to try to get a hold on, especially whether radiation is more important than thermal variations, we need to get this is what's going to be required is an integration of several types of spacecraft data and measurements to get an idea, then be able to constrain how important these processes are. And so the main conclusion is that the weathering out there, there's a lot of processes that are going on that aren't necessarily very well constrained. And we're just starting to get an idea of how powerful these processes can be. And there's a lot of work to do. So I look forward to talking to you all about it.
I'll start off with one. So as you probably know, impact gardening by micrometeorites is one of my favorite things to think about from a physical standpoint.
Right.
And one thing about that is that it will introduce you mentioned that the energy from those impacts could maybe do a little bit of chemical processing as well. I think that's
Possible.
an interesting concept. That would go deeper than something like radiation, which would process mostly just a very bit of the surface.
Mm-hmm.
Would you expect like a gradient of composition?
Most likely. I mean, all of these, especially these mechanical processes versus radiation and thermal processes. The radiation and thermal process will probably, again, just be the very light surface. But yeah, like the estimates so far for micrometeorite gardening are saying like the first meter can end up being processed. And again, the radiation can end up processing deeper depending on the porosity of the ice that you're looking at, because if it doesn't have anything to run into, it'll keep going farther. The energy, cosmic rays can penetrate up to a meter, but of course, when it ends up interacting with the material, that it can end up being much farther down. And so usually when we're looking at radiation on these objects, we're concentrating more on UV, which is really the very near surface, electrons, and any particles that are in the magnetospheres of Jupiter or Saturn or that sort of thing, because that's usually the much higher dose. The cosmic rays, the dose rate is just so slow. It's not necessarily going to be able, we're not going to be able to really see those changes very much. But back to the physical processes, you see I kind of skirted that one, because it's just really unknown exactly how it's going to work, because there could be some amount of thermal input from micrometeorites, but as I've talked with one of my collaborators, you don't cook a steak by shooting it with a gun. You know, there's some amount of heat that needs to be applied to all of it. And so say you have a micrometeorite impact, there's heating right there, some amount of your material vaporizes, but then, and so you could imagine there's a lot of heat there, which would make things turn crystalline, for example, but then there's a lot of vapor that redeposits, and probably at that temperature, a redeposit is amorphous. So for that particular process, it's unclear what the net gain would be from that. And then for sublimation and chemistry, you're creating a lot of vapor, so some amount of it could just escape. But then again, we see how sticky the water is, so whatever materials are in that vapor could just end up recondensing. So yeah, it's especially the micrometeorite stuff. There's not been a lot of studies into it, and also experiments would be very difficult to do. The only thing that I've seen are really, really high velocity impacts into ice. And what was interesting with that is they did crystalline samples and amorphous samples. And the amorphous samples, like there was a very large energy barrier before the actual sample started heating, because the assumption is that most of the heat of the impact was going into the conversion from amorphous to crystalline, which is the opposite of what you would think. Since an exothermic reaction, you think you just need to like bump it and it would just go. But apparently there was this large energy barrier, so that blows my mind. So yeah, unfortunately, well, maybe it is fortunate. There's a wide open field looking into how these micrometeorites process these surfaces, especially because and I've been thinking about this a lot, so this is why I'm going on about it. One of the assumptions is that on the icy surfaces is that we have a regolith that's comparable to, say, what we see on the moon or on Mars. But those are all rocks. You know, the micrometeorites don't vaporize most of the minerals that they run into because they're so low energy as opposed to a large impact. I mean, we're not even sure that it would process things in the same kind of way to make a regolith on the surface.
Just a little follow-up on this. With your sampling mechanism, I haven't gone into Lou's lab recently, but can you actually make these samples and they're portable? If
No.
one could, because you can't.
They're not portable.
No way.
No, not as such.
Because we have the electron gun here, but
Right.
more importantly, Bob Carlson at JPL can actually take a sample and give it the ionizing environment of Europa, say.
Right.
And so you can get information if there was.
Well, in our system, we have a hydrogen lamp that produces UV radiation. And those are important for the thinner samples that are maybe a micron or less to be able to really fully photolize the surface. The entire ice sample, that's about as thick as you can get. Now, unfortunately, for solar system applications, then especially a water ice sample is that thin, there's no features in the near infrared. Those are relatively weak features compared to where near 3 micron, where the fundamental is. And so to get those features to show up, I have to make much thicker samples, anywhere up to like 20 microns thick. But then the UV lamp doesn't penetrate that. And unfortunately, to be able to penetrate a thickness that's that large, you need something in the mega EV range, which is, you know, if you have $1 million lying around, I'd love to buy an accelerator.
So we just now start buying lottery tickets. We read about it all the time.
Do we have other questions?
Since you said you were going to be also studying the Kuiper Belt objects, or you had funding for that, what kind of platforms are being used to gather the infrared data for that, and how difficult is it to kind of determine what's going on there as far as weathering goes, versus getting information such as VIMS from orbiting spacecraft.
Right, and that's the thing with the Kuiper Belt objects. We have infrared spectra from ground-based observing. Mostly, like the larger telescopes can get near-infrared spectra. So I was showing like right around 1.5, and especially that 1.65 micron feature. That's how we try to assess how much amorphous or crystalline ice is there, and by fitting those data. Now, now we'd want to compare that to an idea of what the temperature is on the surface and what the radiation environment is. And unfortunately, unlike the Jupiter system or the Saturnian system, where there's been a spacecraft to actually measure the particles and fields there, we can get a really good idea of what the radiation dose is there. In the Kuiper Belt, we're just kind of guessing. Like when Voyager shot through there, that's about the only measurement that we have. And so there's some assumptions based on what's known about the solar wind and how it should behave out in that area, but it's not very well constrained, the radiation dose on the surface. And then the thermal measurements would be made from Spitzer data. That's an assumption from the albedo of the object, what the temperature is. So say you calculate the albedo, you put an object out that far from the sun, you make an estimate of the temperature, and now that temperature, of course, is the first meter or so at the surface, which could be very different from what the actual ice on the very surface is, considering that ice can be reasonably well insulating. So, not constrained. That's the short answer.
One other, which is that, so different IR measurements are going to give you, different wavelengths will give you,
right.
You're sensitive to a different skin depth. Do you have a broad enough range in, wavelength measurement to say that you're actually seeing a difference in composition with depth on the surface?
Well, and that's the project that I'm just starting, is especially with the NIMS data. That's a reasonably good data set that has, especially in the same data, it has the near-infrared and the mid-infrared. And Gary Hansen, I forgot to give props to Gary Hansen for, he's already demonstrated that with some fits in the 3 micron range, that there's variation in the amorphous and crystalline content across the surface of Ganymede. And at the time, there weren't any amorphous optical constants in the near-infrared for water. And so at the time, he assumed that it was all 100% crystalline in the near-infrared. So that was kind of interesting that in the near-infrared, which sees to a much deeper depth, up to like the centimeter, millimeter range, that's the maximum depth of sampling, that it could be 100% crystalline. And then in the 3 micron, where you're just seeing the barest first micron of the surface, that it would be more amorphous. But that would kind of make sense, because the very surface gets that much more radiation than deeper down. So that was the result that they got. We're taking another look at it now that we actually have optical constants to do a proper fitting in the near-infrared. And I'm looking into it. I was just kind of taking a look at some early stuff, and preliminarily it looked like almost the same, which was really cool, but don't quote me on that.
That's great. Other questions, or let's thank our speaker.